And at this point, we're going to be focusing on hyperbolic partial differential equations. It's going to be our focus for the remainder of the this works. B. Yeah, okay. So what we have here for our, and I'm going to try and keep this here. I'm going to try and present to you the fundamentals of the characteristics of hyperbolic partial differential equation. And I also will be talking about summary equations and some simplification of summary equation that leads us to kinematic wave approach. And then after that, we are going to implement kinematic wave in this next cycle. So again, we're going to follow the same strategy, give some perspective on the equations we're looking at, and then we're going to apply that for our solution. Okay, so summary equations is a type of hyperbolic partial differential equation. Hyperbolic PDE partial differential equation are those when we evaluate b squared for a c, this number is larger than 0. The example I provided, what we had was something like that. Partial of u with respect to d double derivative minus partial of u with respect to the double derivative of x is equals to 0. This is the wave equation. It's beyond the scope of this class, but you can actually demonstrate open channel flow equations, closed pipe flow equations from this double derivative equation through substitution of variables. We can establish a link between this equation here and say closed pipe transient flows. So much so that back in the 1940s, actually I think it starts in the 1930s, people would develop. Do you guys know what hydraulic transient is? What a hydraulic transient? In Portuguese, the term is log germination. I want to study it again. So so the first formulations to solve water hammer log germination were graphical approaches. Those graphical approaches go back in the 30s, 40s, and 50s, and it was essentially a solution of physics. So they're solving closed pipe transient flow, but actually what they're solving is a wave equation. Parmentian is a good reference for this type of analysis, both of Parmentian. Classic, both in the 1950s and 1960s, he wrote about transient closed systems. But hyperbolic PDEs, nowadays, they're mostly connected with three groups of equations. So, let me put here three arrows, and those are very commonly used. One, we have an Navier-Stokes equation. Navier-Stokes equation is not truly a hyperbolic system because it has on the right-hand side. So let me write one of the Navier-Stokes equations. So I have, say, partial with respect to u, t, then I have the convective acceleration. Then there will be Other terms, let me write this as if it was a 1D. So I have local convective acceleration. Then I will have here a gravity term. But I will have also a diffusive term here. And so forth. This term here is an elliptic term within the Navier-Stokes equation. So Navier-Stokes, the left-hand side is a hyperbolic system, the right-hand side is an elliptic system. Solvers usually have two modules to solve Navier-Stokes. One of the modules is a Laplace equation like solver like we did to handle the dissipation component. And the right-hand side is a hyperbolic solver like the one we're going to construct now. So there are two things in separate. Another commonly hyperbolic PDE is the shallow water equation. And the Euler equation. Shallow water equation, Euler equation, they're both innately multidimensional. Shallow water is xy, depth average, and d. So x, y, and d. Other equations you can have x, y, c, and d, x, y, just x. So each Euler equation is very flexible. Euler equation is actually the origin for Navier-Stokes equation. If you cut this term from Navier-Stokes equation, what you have left over is the Euler equation. So essentially, Euler equation was the origin for most of the formulations we use for open channel flows, for gas flows. Euler equation is the origin. Then we have another one. Góes equation, which is not so popular, not so often found. Góes equation has advantages over Sundman equation in that it allows for vertical acceleration to be represented. And finally, we have Sundman equations. Interestingly, these two men worked together. Góes was younger, by a lot, but younger, and Sundman, both were professors. And another interesting fact is that Sundman has also provided contributions to structural engineering. So if you ask the structural engineer, give us an equation. Oh, yeah, I know. If you write an equation, it's completely different from what you know. The Sundman equation became the workhorse for most of open channel flow simulation production. It's a workhorse. And simplicity is one reason, computational cost is another reason. But over the years, people have approached Sundman equations in different means, different ways. Simplifications, if you will, for the Sundman equation. We can say that nowadays we are in our fourth generation of Sundman equation solvers. Fourth, yes. Why? Because the first approaches for Sundman equation involved simplifications that led to what we call now kinematic wave. Kinematic wave equation is a type of Sundman equation that I'm going to explain today. We're going to create a solver for that today, but it has specific limitations. So there are disclaimers about this equation here that we should be aware of. Over time, simplifications were less stringent, and people created what is called diffusive wave but others more correctly called zero inertia wave. Zero inertia wave equation, which is a little more time-consuming and laborious to create. So we are not presenting here today the zero inertia wave equation. Then there's the full equations, the full solenoid equations that were put in place for, I'd say, maybe people start back with those equations. Normally, the full versions in the 1980s, 1990s, people start solving this. Nowadays, since 1992, a researcher from aerospace engineering, Góes, adopted the technique used in our equation solution that gives much better results, and adopted this technique to solve some equations. And that ushered version of some equations is a full equation approach with no linear schemes. So understand, it's not that the solenoid equations are changed. What is changed is the way we solve it. We solve it nowadays with those nonlinear schemes. They are also known as approximate Riemann solvers. And those are really much better. The outcomes and solutions are much more reliable, much more robust than anything that came before. But it's not necessarily a change in the equation. It's a change in how we solve it. Everything we solve, everything that until this point here, were normally solved in finite figures. From this point onward, we have adopted finite volume, and those schemes were completely, up to this point, were completely foreign to civil engineers, where more computational physics, in aerospace engineering, and finally now within civil engineering. So our focus today will be on some equations. Any questions in here? Okay, so I'm going to erase the whole thing. So I'm going to write here a version for some equations that are valid for prismatic channels, so channels that the cross section will change, and channels that don't have lateral contributions, meaning that the channel is not losing water or it's receiving water from the banks. And there are so many details. For instance, I can write, and you need to find many books that are going to represent some equations in terms of y or h, depth, and velocity. Okay? If you find some equations written this way, we call this primitive variables. So it's a solution used for primitive variables. But if you find some equation written in A and Q, area, cross-section area, control A, we refer to those as conservative variables. Now, when there are no discontinuities in the flow has no naturally occurring discontinuities, because that's one characteristic of hyperbolic fluids. Even if at the boundaries the conditions haven't really changed abruptly. In the middle of the solution domain, a discontinuity may occur naturally. Mathematically speaking, it shows that in the physical world, the real world, for water flows, those associated charges of hydrogens. Hydrogens may appear in the solution naturally. Even if at the borders of the system, your conditions are not discontinuous. If a hydraulic gel appears in the solution, predictive variables will give you the wrong solution near the hydraulic gels. So if you want to have correct solutions everywhere, you need to move to conservative variables. Again, it can be proven. What I'm telling you is something that you can mathematically demonstrate. But it's not the scope. This class is about solving those equations, not theoretically discussing them. We're going to choose conservative variables. So when I'm writing certain equations, it's essentially a system. This is, and if I turn this on, okay, let me see if I can do that. Okay. And this doesn't work. Really? Yes. Okay. It's a system of PDEs. Most of the equations I presented here are a system of PDEs. One refers to conservation of mass, and the other is conservation of linear momentum. So this system of PDEs can be referred to and be expressed mathematically like that. That's conservation of mass. So the derivative with respect to time of the cross-sectional area plus the derivative with respect to space, partial derivative of the flow rate equals 1. One of the best sources for you to study that derivation would be the book by Professor Stern, 2001, Open Channel Hydrology. The second equation is this. Partial derivative with respect to time of Q plus partial derivative with respect to space of Q divided by A, Q squared divided by A, plus G, area, centroid value. This is the entire partial derivative with respect to S, and this is equal to G, A, the difference between the dead slope and the friction slope. Now, let's break this down. First, we engineers, we tend not to be very rigorous with mathematics. Okay. We write differential equations sometimes in a free form, way we want. You're going to find some people, even well-established people, that will tend to write this term on the left-hand side and set the equation to 0. And you think, okay, what's the matter? What's the problem of that? Is it wrong? No, it's not. But there are few things here that are important with ordinary differential equations. See, this equation here has 0 on the right-hand side. We call those types of partial differential equations homogeneous. Homogeneous PDEs. Homogeneous means that they don't have source term. What it means, source term? Well, this is the source term. And you can see that the only way for the momentum equation, which is this guy here, should have 0 source term is when you have an open channel situation that is horizontal, so bed load equal to 0, and is frictionless, that the friction flow equals 0. Ideal situation. Imagine, then braid in this form, extremely smooth and horizontal. When I have something like that, this is good for us to study, not real world, but this is to study, because it enables us to create solutions that are not quite analytical solutions. So, if that whole thing here was 0, you can actually derive an analytical solution for a dam break. So we call it the dam break in horizontal frictionless bed. Solution was derived the first time in 1899 by Rieger. Same guy who wrote the method to create trusses. Rieger. He derived also a method to create dam break solutions in frictionless horizontal beds. Analytical for years. So tomorrow we are going to solve those equations, complex equations, in a homogeneous fashion. So I'm going to zero that, and I'm going to solve it. Okay? Today, I'm going to solve this equation here with a very strong simplification on the second equation. Simplification that leads us to what we call kinematic wave. Now, has anyone here applied or derived the kinematic wave equation before? So, anyone heard the term kinematic wave? It was a British mathematician in the 1950s called Lightfield. This guy was, I recall correctly, was the guy who proposed the kinematic wave. And kinematic wave could be applied to traffic flow in the highway, cars, avalanche phenomena, so many different hyperbolic phenomena. So when next time when you are stuck in a traffic jam, think that you are in a hyperbolic flow situation, because you are. You know the equivalent for a hyperbolic in a car setup, traffic setup, the equivalent for a dam break is a red light. So you are waiting for 5 minutes behind the red light. There are thousands of cars behind you, and the highway is empty. When the traffic goes green, start pressing the go. But the guy behind you doesn't go in. He has to see you go before he starts stepping. So there is a very strong, so many analogies between traffic engineering, traffic flows, and water flows. So a red light is a dam break equivalent. But anyways, so let's talk about kinematic wave. Any questions so far? The point being is that if you don't have differential terms, put on the right hand side. Those are your source terms. You have to identify if they are 0 or if they are not 0. A lot of engineers, as I said, they will put this on the left hand side. Use the left hand side only for differential terms. That's how you properly write partial differential equations. Okay, kinematic weight. So it seems almost funny when I start deriving kinematic weight. It looks pretty funny. So the kinematic weight, I'm going to neglect local acceleration. But you just consider this as important. I'm going to neglect the convective acceleration. And if I had stopped here, if I had stopped at this point, I would have gotten what's called a zero inertia. But no, I'll neglect the free surface disposal. What's left, right? So you cut everything on left and side. So what's left here? Well, what's left is this. 0 equal G A S0 minus SF. And then what you do? Okay, I'm cutting these two. So right? S0 equals SF. Can someone give me a physical interpretation of that? Those of you who study open channels, what S0 equals SF means in the real world? So, let's continue. Keep going. What it means? So uniform flow, energy, slope, or friction flow, paradoxical flow. It's all right. All correct. But remember that this equation here still stands. I'm here, not here. This equation here still stands. So I'm going to add those two things together. But the kinematic wave, canceling those terms, it means that those two terms are more important than the other terms. Those two terms dominate over the other terms. Okay, so what are those two terms? Physically speaking, what do those two terms represent? Remember, this is conservation of linear momentum equation, correct? What's the other name we give to the conservation of linear momentum? There's a shorter name for that. What's the other name for this? Conservation of linear momentum, B, short. What's the other way we call this? Force equals mass times acceleration, right? Well, not quite. Change in linear momentum equals the summation of resulting forces. That's what we know. Okay, so this is Newton's second law, right? So what does this mean? It means that every one of those terms here in this equation means something in Newton's second law. As an anchor in Newton's second law. Newton's second law talks about acceleration, right? So change in linear momentum. MV, VE of MV, linear momentum. Change. For solid mechanics, we call it acceleration. But for fluid mechanics, we have three types of accelerations happening in fluid, right? Anyone recalls those three types of accelerations we have in fluid mechanics? One is centrifugal. that solid mechanics also have centrifugal acceleration, right? Force, so the ball involved in a circular trajectory. The fact that the ball is changing is vector, the angle of the vector, it requires you to pull, otherwise the ball goes away. So there's a force there, and there's a change in the pulse centrifugal acceleration. The other acceleration you have in solid mechanics is this, local acceleration, the dV/dt. What's the other acceleration you have? Convective can only happen because you can squeeze the fluid, right? And the convective acceleration is here, this term. Okay? This is the pressure gradient created by the free surface slope. So what I'm telling you is that when I'm canceling all those terms in kinematic wave, is that I'm neglecting the inertial terms of acceleration. So locally speaking, the acceleration isn't so important. I'm neglecting the free surface slope because the most important things I have are friction forces and the gravity forces. Those two terms here are friction and gravity. Those are the dominant. So in the real world, what application do you think that this assumption is best applied to? Which types of application do you think kinematic would be most properly used? If there is no backwater effects, and if the sewer would be very steep, yes, combination of those two. Steep, but you can have backup overflow. You can have backwater profile. If you have a backwater profile, then this term here is important. You can't neglect that. Other application. Parking lots. Rains in the parking lot with snow. It's asphalt, pretty rough. A lot of roughness in the asphalt here makes this very important. But the slope of the parking lot is usually measured in degrees, not in a fraction of degree. You're looking at 1%, 2% slopes in the parking lot, pretty steep. So flow in the parking lot or in a gutter, so you have a gutter in the roadway, you're looking at what's flowing in the gutter. It's pretty steep as well, typically concrete, which is terribly rough for this rubber. So flow in the gutter can be well described with the kinematic wave. If the gutter is finishing on an inlet, and the inlet is not blocked, it's not clogged, so the water flows freely in the inlet, and there's no back water in the gutter, you know what the term I'm using, right? Gutter is sacheta, inlet, boca de lobo. So if those terms, if the inlet is not blocked, then the flow in the gutter goes there, and kinematic waves is the application. However, you have to understand that if I write well, even though this is a valid way to represent the kinematic wave, back in the 1950s and 60s, when people solving this in computers, it was not convenient to solve flows with two variables. So the kinematic wave, we're going to make an effort to represent everything with Q, not with A and Q, but only with Q. So some of the demonstration we're going to present now have now the goal of eliminating A from our solution. All right. Can you give me one equation that we use frequently that relates A and Q? Here. This is a B. One equation that uses A and Q. We call it, starts with M. Magnitude. Yes. So if you write this in SI units, it's going to be 1. If you're writing this in English units, it will be 1.49. Let's write in SI units. It will be 1 over N, area, hydraulic radius, slope. And I'm not going to put here slope S0 or SF because both are the same. I'm just going to write S. Which is, well, I can also write all right. So I don't have hydraulic radius anymore. Hydraulic radius area divided by whack perimeter. And I'm going to introduce a simplification right now so that we can make our Excel file faster. It doesn't have to be this way. What would be this equation for a wide rectangular channel? How this equation would behave for a wide rectangular channel? Wide rectangular channel cross section is like this, right? So I have a very large width of the channel, a very small depth of the channel. Okay, what is the hydraulic radius for this guy? How can you approximate hydraulic radius? Why? Because hydraulic radius is area, which is W times H, divided by the wet perimeter, which is W plus 2H. But given that 2H is too small by comparison to W, I can neglect this guy. I can cancel these H's in hydraulic radius equals H. Right? So, and what about area itself? Area is equals W times H. So if this was for a wide rectangular channel, and remember, I am doing this not because I must, just because it's easier for me later to write the Excel code. Okay, I can work with that. I can do that. But I'm going to make a simplification. For a wide rectangular channel, then Q equals 1 over N W times H to the power of 5/3 square root of S. Is right? Okay, so then I have a relationship between Q and A, but I'm writing this in terms of H for now. So I'm going to keep this development there. Now I'm going to center my attention here. Partial A with respect to time can be written as the total derivative of Q with respect to A times partial derivative of the partial derivative of A with respect to time can be written as the total derivative of A with respect to Q times partial derivative of Q with respect to time. I'm changing this variable so I can replace A in this equation here with Q. So I'm going to combine those two equations. And then I have total derivative of A with respect to Q times partial derivative of Q with respect to P plus partial derivative of Q with respect to X equal to 0. Which then I can rewrite as partial derivative of Q with respect to time plus total derivative of Q with respect to area times partial derivative of Q with respect to space leading to 0. We're back in calculus, right? So you're entering the class thinking about numerical methods, and now you're in a trapped in something that looks like mathematics. Oh, it is mathematics. So this is essentially mathematics we're looking at. Can someone give you the units of this term? PQE. What's the unit? Unit per second. Unit per second. Length per time. Velocity. So this is a kinematic wave scenario. Okay. How am I going to derive this term? Here to derive this term. Okay. So the derivative of Q with respect to A will come from this equation. So dQ dA, I'm going to take this term here, and I'm going to, because this is constant, right? The perimeter for a second here, if I'm considering a wide rectangular channel, the perimeter is essentially width. So it's constant. And slope on side. So this would be 1 over n times the width raised to the power of 2/3 times square root of s. So those are the constant terms. And then I have a derivative of a raised to the power of 5/3. So what would be the derivative of this guy? A raised to the power 2/3. Isn't it? Am I doing something wrong here? So, writing this again. This is going to be 5 square root of s slope, that slope, many n, width of the channel raised to the power of 2/3 times, well actually it's 5/3, so 3. And what means area? Width times W, right? So here I have H raised to the power of 2/3. And then at that point, I could cancel W, right? Cancel W. So that would be 5/3 square root of S and H raised to the power of 2/3. So what is this term again? This is for a wide rectangular channel. This is the kinematic wave celerity that I'm going to use here. Finally, dq dt plus 5/3 square root of S n times H raised to the power of 2/3 times the partial derivative with respect to x equals to 0. So this is the mathematical model that we will implement. Mathematical model will require us to use a numerical method, finite difference, a numerical scheme, so then we can write these equations using Excel, Visual Basic, C++, whatever the language. How can we write that equation? So we're going to repeat the error of I'm going to repeat the error by Richardson, and we're going to attempt to write an FTC axis, knowing it's going to crash. FTCS, 4 times center space. So my derivative with respect to time, dq dt is going to be qij plus 1 minus qij divided by delta t. Centered space, we're going to make an average, actually the difference between I plus 1 and I minus 1. So that would make partial q with respect to x being equal to qi plus 1 j minus qi minus 1 j divided by 2 delta x. So we're going to try that. And this is going to fail. Second thing, the second approach we're going to try is this. Is called first order coupling. Instead of making the use of I-1, we choose I. And then divide by just delta x, not 2 delta x. Okay, small change, relatively stable. Mind-boggling. Can be shown mathematically. So what does this mean here? So when I'm looking at the mathematical model, this means this. Qi j plus 1. So I'm going to make the FTCS. Qi j plus 1 is going to be equal to Qi j plus. I'm going to send everything to this right hand side. Bp divided by dx. 5/3 square root of s divided by n, h to the power 2/3. H to the power 2/3, then open the parentheses, Qi plus 1 j minus Qi minus 1 j. So this guy here is not delta x, it's 2 delta x. So we're going to create an Excel solver that we're going to solve cell by cell this equation, starting with a known condition. We're going to start with a certain flow. So we have to begin our calculations with C uniform flow. At the upstream boundary, I'm going to create an inflow diagram. I'm going to speed up the flow and lower the flow at the entrance of the channel. And then I'm going to see how this flood wave will propagate down my channel. That's what I'm going to do. This is the kinematic wave. You need to copy that equation because when I'm lower the pattern, you're not going to be able to. You're not going to be able to see.
Sure. Almost in that the equation is for right rectangular.
Yes. So what this would have been different if it wasn't the case, right? With that derivative here would be a little more complicated. If you had a rectangular channel, just make it a thing. If I had a rectangular channel with H and W that are comparable, okay, but fixed W. So dq dA is the same as writing dq W dH. That will happen the same for rectangular channel. And then area 5/3, perimeter 2/3, So that would have been, so the constant terms remain constant. Square root of S divided by N, but then area 5/3, right? So I have to make a derivation B, BH of, and that's the one thing here. I'm not sure if this W here should have appeared there. I'm not remembering by heart. Just 8, because of this step here, if this 8 should have been here, but equation-wise, that will work. So now I have to make a derivation of this term with respect to H. So I have here W H raised to the power of 5/3 divided by W plus 2H. So now I have to make this derivative here. W comes out, if you remember, the derivative of two functions f and g. The f prime g times f g prime divided by g squared. What was the form of word? False. Not remember this is the right form for this derivative, and I have an f and g function. Huh?
Minus.
What?
Minus.
Minus it. This minus this divided by g squared. So in this case here, f prime equals w, right? G prime equals 2, so that would be w times w plus 2h minus w h, the derivative of this guy here would be 1, no, 2, divided by this term here squared, which would be w squared plus 4wh plus 4h squared. And then simplify. The reason being that can we do that? We can. It's just that things become very more complicated to implement.
But it's also kinematic wave or not?
Well, this is kinematic wave. It's just the cross section geometry is simplified. Not rectangular. You can write kinematic wave also for triangular cross sections, for circular cross sections. It's just that the geometry relationship between Q and A becomes more complicated. For a rectangular channel, this is what we have. There are ways for us to simplify this. You can simplify this. For instance, this 2WH here term cancels out this. So that would be W squared on the numerator divided by this term. So yes, you can start simplifying this. But then but visit this equation for the solution. So we're going to implement that. This equation here, the kinematic wave, FTCS, kinematic wave, is what we're going to try to do first. So we're going to try to implement this equation here in Excel. To do this, I'm going to turn on the screen again. Can I lower the panel? Não vai fazer um braço. All right, we're back in business. Opa, yeah. So I am pulling here the result from a different material, but it's not shown. So this is a different material, not the one we have used so far that I'm discussing. What we have here is an alternative derivative for the QDA. The difference from this one here is that here I have used age as a variable. And the disadvantage of this is that I have to compute age for the values of Q. So I could use this method here. But this one, I'm not using age. I'm using the actual value Q for a replacement. And let me see how this was derived. Maybe we're going to make a change on the So look at this expression here for the area. So area, when we isolate area from the many equation, right? Like we did before, but if I isolate area, then I can have this expression instead. If I make the derivative of Q with respect to this equation here, then I obtain this formula here. So the derivative of A with respect to P, basically increase the zoom. The derivative of A with respect to P will lead to this expression. And the inverse of this expression here would be more convenient for us to put in a kinematic way. So this expression here, it is better than what I've just derived. Both are correct, but this expression here, I will need to keep track of H, and in here, I'm just handling Q. So let's use this instead. Let's use this expression here instead. So what does this expression here means? Q I equals 1 be equal to Q I J plus delta E divided by delta X to delta X. Then multiplied by this term here, which would be 5/3 square root of S naught divided by many number multiplied by the weighted perimeter raised to the power of 2/3. And in the case of a wide rectangular channel, the weighted perimeter can be approximated by W, which is the width of the channel. And this will be multiplied by Q raised to the power of 0.4. So that would be Q I J. This number raised to the power of 0.4. Okay? Oh, take it out. QIJ Then I'm going to multiply by the difference, the gradient dq dx, which is q I plus 1 j minus q I minus 1 j. So this is the expression we're going to use for the fourth time centered space, and it should fail this expression. This is the expression we're going to use for the first order upwind. And this one will not fail. Interesting. However, if you remember other expressions other equations we solved before in this course, we know that there will be a certain time step after which the code becomes unstable. Right? We saw that even yesterday with the diffusive parabolic problem. In this case, what controls the stability of this code is called the Courant condition. The Courant condition states that our time steps so another way of saying is that a numerical time step is dx dt. So the delta t, or delta x delta t, our delta x delta t should be the threshold for stability is to ensure that this is less or equal than the other term that we have, velocity, to be dq dA. Oops. So if we exceed that, our numerical code will become unstable. So for the kinematic wave, this implies that our time steps should be less than this. All right, so let me ask you a question. We're going to be dealing with calculations that are going to vary flow rate Q over time and over space. Okay? And as you can see here, the time step requires us to keep delta t under a certain number. Delta x is discretization. We can make it fixed. Many roughness, slow, everything is fixed. But Q isn't. Q is a variable. How do you suggest that we ensure that our delta t will never exceed this threshold? I have a suggestion. We are going to route a hydrograph in the channel, right? We can ask the user, what's the peak flow? So what's the peak flow that you're going to have in this hydrograph? And if I have the peak flow, I can use that peak flow there. And then always sure that my delta T is always under, because if I had here as big flow, you agree with me that delta T is going to be the smallest possible number. If this number here is not a peak flow, it means that I could have made the calculation with a higher delta T, but I didn't. The code is still stable. So, in a real kinematic wave, if you're solving a kinematic wave, you can look at the previous time step and look, okay, over my channel, in the previous time step, what was the peak flow? And then adopt that previous time step value here. But for an Excel solution that's simpler, you can ask beforehand, okay, peak hydrograph is going to be how much? And then we introduce that. Okay, so we're going to keep this as our test to ensure that our code is not failing. So I'm going to write this equation here. Delta T is going to be, and I'm probably, if you guys want, I can send this Word file with those equations to you. Or I can send the other document, but the other document is 180 something pages, and maybe just have this together. So delta T equals delta X divided in a large expression. 5/3. I can copy this here. But in this parenthesis, I'm going to have an exponent of 5/3, 3/15. Raised power. Well, the good news is that this entire term here is constant. W is constant, S naught is constant, everything here, Q peak is constant. So you can calculate delta T before you start the calculations. So this is all constant. And then you start your process, calculation process. Now, if this wasn't a wide rectangular channel, then we would need to keep updating delta T, because that W here wouldn't be the perimeter anymore. Perimeter would vary with that. It gets a little more complicated. Okay, so time for us to apply those equations here in Excel. Let's create this file from scratch now. Let's make a channel length. Yes. o hidráulico, sim, perímetro dado. So channel length would be, say, 5 kilometers channel. Channel slope. Remember that channel slope are supposed to be pretty steep. I'm going to make it 2%, no, maybe 1% slope channel. So a 5 kilometer channel, 1% drops 50 meters in 5 kilometers. Pretty steep. Meter by meter. Channel roughness, I'm going to put 0.035. So that's many roughness. Channel width. I'm going to make it, if this is going to be a wide rectangular channel, I'm going to make it wide. I'm going to make it like a 10-meter wide channel. Discretization points. So how many discretization points I'm going to have? Let's put 100. 101. So then I have 100 reaches. What else? Okay, as far as input goes, this is it. But now I need to have information about the upstream hydrograph. So what's the condition at the upstream flow? We're going to make a triangular inflow hydrograph. So let's make a hydrograph that looks like this. So this is time in seconds, and this is the flow rate in cubic meter per second. So maybe at 0 seconds, I had a flow rate of, say, 2 cubic meters per second in the channel. Then at 30 minutes, the flow rate has jumped to 15 cubic meters per second. And then at an hour, it has come back to 2. So triangle, go up to 15, go back to 2. What is the equation that does that? So between 0 and 1800 seconds, Q over T is going to be equal to 2 plus T minus 1800, no, T divided by 1800 times 13. So when I get 1800 seconds, I am already at 15 cubic meters per second. So between 1800 seconds and 3600 seconds, which means an hour, Q will start at 15 minus 13 P minus 1800 divided by T times 13. So when I am at 1300 seconds, 3,600 seconds or 3,600 seconds, I am exactly at 2 cubic meters per second again. But I have to ensure that it doesn't drop below that, so it's going to be maximum between 2 and this number. So this is the function that I have to use at the boundary condition. So Q1 will not be calculated with the equations I present. Q1 will come from this equation. Q2, Q3, Q4, everything calculates with the formula. But Q1 comes from here. Okay? So can everybody understand what I did here? So I'm putting a line. So the second equation, when t equals 1800, the numerator is 0. So I have 15. When t equals 3600, the numerator equals 1800. This is not going to work. Yes, sorry. On the end. This is 1800. Yeah. Now this works. Because when I have t equals 3,600, the numerator is going to be equal to 1,800. The denominator equals 1,800. So 1 times 13 minus 13, take 15 out, I have 2. So this is the equation for the recession curve of the hydrograph. Okay? So this takes us up, and as a result, I know what the Q peak is. So what is the Q peak from our hydrograph? Q peak equals, in this case, 15 cubic meters per second. Okay? And you can change this hydrograph. You can create any function you want. It's just that you have to update in your Visual Basic code how you're going to make this code. It can be done. It's easy. So I will do here one calculation because I can do this ahead of time. And it's not going to hurt to calculate delta T. Delta T is going to be equal to this function, right? The lower function. But to calculate this delta T, I need to calculate delta X. So, let me put here delta X. Delta X, you agree with me, is going to be the channel length divided by the number of discretization points minus 1. So my delta X is 50 meters. Then delta T will come from this expression. And I have everything. So this is going to be delta X divided by 5/3 times S naught, which is this slope, raised to the power of 0.5, divided by, there are 2 terms, meaning roughness, times width of the channel, raised to the power of 2/3, which is going to be thirds. I close the denominator, and I'm going to raise this to the power of 3/5. And I'm going to multiply this by QP, raised to the power of 0. So according to this formula, I need to update calculations every 13.6 seconds. That's the maximum that I can use when I have the peak flows. If I didn't have the peak flows, I could have a larger delta T. But I want to calculate one delta T and use this throughout the calculation. I could have done that also with the VBA code. But since this is going to be a fixed number, I can do this ahead of time. Yeah. Let me zoom. Did you guys got the same time step as me? 13.6. Okay? Is it okay if I go on? Okay, if this is okay, I'm going to continue here, okay? All right, so now we're going to add the command button to start the calculations. So the command button, we're going to developer. By the way, before I do that, let me save this Excel file as like a macro-enabled Excel file. File, save as, and I'm going to call that kinematic wave. Kinematic wave, and it's going to be Excel macro-enabled workbook. That's the kinematic wave solver. I will now add here developer, insert command button here, change the properties of the command button. I'm going to call this KW. KW is a short for kinematic wave. KW, and I'm going to call this command. So channel routing. Okay, we're going to solve, channel routing. When I'm solving the channel routing, let me tell you what my strategy to write those results are going to look like. If you remember yesterday, solver, I had the columns to put the spatial coordinate first point, second, third, and so on. The spatial coordinate here, align, was my x-axis. The vertical was where I'm writing the result over time. So this is what I'm going to do again. So when I am writing this, the first column here will be time. And the other columns here will be the coordinates. I have first, second, third delta x, fourth delta x. So I'm going to write here, the first one obviously is 0, is the boundary condition. Then I have 50, 100 meters, 150, and so forth. I'm not going to write it by hand. I'll have the code write this for me. Okay? Because if you change this here, this will have to be changed automatically. I'm writing this at line 13. And then over time, I'm going to write here the results. What do you expect to see here? So that would be Q1, right? Q1 results. Q1 results, which is x equals 0, what you're going to have is that triangular result. Downstream from this point, we're going to see the flood routing going through the channel. Okay? So here is a boundary condition. What is the initial condition? What's the initial condition that we have? Our initial condition, the channel, the entire channel is flowing with a flow rate of 2 cubic meters per second. Right? We told that. So it's starting at 2, goes to 15, and then goes back to 2. That's the original condition. So I'm also having the code. You see line 12 here is going to populate line 12 with, actually, no, I'm going to move this one down. So here I'm going to write coordinate in meters. So I'm going to write the coordinate 0, 50, and so forth. I'm going to write the initial condition. You can have a channel that the flow rate is not uniform in the beginning. It could be different. It could be whatever. And then I'm going to compute for every time here what is the conditions for it. So let's do that first. Let's do first populate those results in my Excel file. So when I double click this guy here, actually when I add code, we need to define some variables as usual. So first variable I'm going to define is going to be channel length, width, slope, the main number, delta x, delta t, yeah, that's it. As far as double variable goes, as double. And then I need to define some vectors. I'm going to create a vector here for Q, maybe up to, say, 1,000. Qn, which is the new variable of computing, using both variables, both as double. And if you wanted, you could calculate the area based on Q. Now that I have computed all values for Q, I could back compute the values for A and depth and everything. And if you want that, then you have to have vectors for the others too. But here I'm just computing Q. Right? So read input data. L is going to be cells, two, value, actually even value. That's not cells, 3, 2, with roughness, cells, 4, 2, with cells, 5, 2. BP, cells, 9, 2. BX, cells, 8, 2. So this is, you know what I should have put here? Looking at this, I should have created a line for steady flow, Q steady. So let me add this here. Add that line. Q steady, so steady state flow, 2 cubic meters per second. So then I can look at Q, create here a Q steady, maybe Q0, 0, O, Q naught. So Q naught in steady flow, which would be cells 7, 2. Then Vx is 9, 2, and Vt is 10, 2. I need also to define some variables for the numerical calculation. I'm going to define two variables here: dim, II, and n nodes as integer. So n nodes, as you know, is the number of nodes for calculation, discretization points, 101, and II is going to be used for index on calculation. So what is n nodes? N nodes is here, right? Cells 6, 2. So n nodes for cells 6, 2. And I think I finished my input data. All right? So next block of calculation is what we'll call steady. Steady here could be a gradually varied flow computation, anything that you have to do that's not time evolution. So the preliminary calculations. Preliminary steady calculations. For instance, you could have done here the calculation of BT if we wanted to. But since we already computed BT, we don't need to do that. But we could have BT calculated right there. What I'm going to do is just this. I'm going to state for II equals 1 to n nodes. Next. I'm going to do this. I'm going to make QII equals Q naught. And I'm going to call the new values for the flow QNII equals to Q naught. So I am forcing here the steady value to be applied everywhere in my channel. Next will be the unsteady flow loop. And that reminds me that we have not told our code when we stop the simulation. So for how long we're going to simulate, right? We haven't told this. So TSIM, we haven't asked. So we have to ask here, maybe after VT and here. TSIM. What's the simulation time? In seconds. Maybe we're going to simulate a little over an hour. Maybe 4,000 seconds for simulation. And then I have to put here after dt, I have to put t, and I have to put tc.
How is the value of simulation time?
4,000 seconds. So, unsteady loop. The first thing I'm going to do in a steady loop, I'm going to start timer telling t equals 0 in the beginning. Then I'm going to make a do while. I don't know the number of time steps, so I'm going to do like I did yesterday. Do while t is smaller than tc, and then we have a loop. I think that's the right or
TC is equal cells somewhere.
I don't remember. Let me open the code. Is do while or while loop? Do while like this, right? The syntax. Do while. Okay, here it's pretty simple. What I need to do is to calculate what is going to happen in the first node through the equations, and I have to calculate the internal cells. Now, what about the downstream node? In the kinematic wave, there are no effects from the downstream propagating towards the upstream. Never there is this effect. So even if there's a backwater really happening in the real world, the kinematic wave equations, as I showed you in the summary equation, don't see that. Numerically, it doesn't matter what happens at the very last node. So the very last node, say node 101, we can copy whatever we have in node 100. It doesn't really matter because it's not going to affect the calculations. However, if this happens to be a true problem that there are backwater profiles, this should influence the upstream end, then you can't use kinematic wave. You have to use a different set of equations. Okay? So I'm going to do this. I'm going to solve the boundary conditions first, which is just a simple set of equations. Then I'm going to solve the internal cells. So how are we going to do that? The first thing, I'm going to update t. T equals t plus delta t. Update that. Then I'm going to address the upstream boundary conditions. Meaning that I have to calculate the flow conditions at the upstream end. This is the same as writing the following. Q n of 1, first node, is going to be equal to 2 plus t divided by 1800 times 13. However, this is equation that's only valid if I am prior to 1800 seconds. So I have to put this in an if. Essentially this. If T is less or equal to 1800, then Qn equals that. Else, so on another case, it is not true. I have to write Qn equals 15 minus T minus 1800 divided by 1800 times 13. But it can't be that either, because if I put that, it will give me negative flows after some value of T, which is not true. So I have to use that maximum expression. But maximum is not something Visual Basic has, that Excel has. So I do that. Work function. What's the syntax again? Worksheet function. I don't remember. Oh yes. Maximum between 2 and this function. Worksheet function. Maximum between those two numbers. So if this number here becomes less than 2, I'm going to go back to 2. So maybe better yet, instead of using 2 here, would you agree with me that this guy here, 2, could be equal to Q naught, the static flow? And here could be Q naught. Right? And here, if I had defined the variable for Q peak, which I have here, and I could take this from cells 8 to 2, I could have written this guy here as Q peak minus Q naught. And here would be Q peak, and here would be Q peak minus Q naught. I'm making the code more generic, so I'm not tying this essentially to those values I created. The only thing that I would need to do is just to adjust the delta T, but the delta T there is adjusted. The other thing to make this even more generic, you see I'm using here 1800, I'm using here 1800. If the hydrograph duration of the rain event is different, I could have this here introduced and change the code and make this even more generic. So I'm making few adjustments here just because I already have the data. Why not use it? All right? So that's an upstream boundary condition already defined. Shame on this. All right, so let's go back there and read TCM. Simulation time is on cell 11. Cells 11 2. Thank you. Okay, any questions on the upstream boundary condition? Everybody here good with that? QN of 1. Thanks. The first QN. You know, there's another thing we haven't done, and we have to do before this. Remember that I have to populate here the coordinates and the initial flow. All these numbers here have to be introduced, and we haven't. So let's write this. So I'm going to put here preliminary instead. You know, since I'm going from here to there, I'm going to write here cells. So what cell specifically? On row 14, starting at the second column, I'm going to write the coordinates. So cells 14, II plus 1. So when I start, the first cell is actually I'm writing the second column. Value. What should I write there? Coordinate. Right? Coordinate starts at 0 and goes all the way to 5,000. So it would be here II minus 1, because it starts at 0, times dx. So when I am at line, the column is a column 102, right? No, 101. Then I will have 100 times 50, so that will give me the coordinate 5,000. That is row 14, the coordinate. Now I have to write the flow rate at row 15. So row 15, just copy that. Row 15. So from column 2 to column 101, 102 actually. This is going to be equal to Q0. It's just the same steady flow everywhere. All right. Downstream boundary condition. So the upstream boundary condition, we have an inflow hydrograph. The downstream boundary condition, we have just copy upstream flow onto it. Meaning that I have Qm of n nodes is going to be equal to Qn, or actually not Qn, Q of n nodes minus 1. So I'm just copying the previous result, previous time step, into this node. All right? Most important is internal cell calculation. So I'm going to make one thing here. I am going to use the first order upwind first, because after all this job, if you create a code that crashes, you're going to kill me. So let me create a code that shouldn't crash and see the results, and then we can switch that to the FTCS that will crash. So here, internal cell calculation. What should I do here? I do this. For II equals 2, so because the first node, I have the result, I don't need the first node. II equals 2 n nodes minus 1, because the very last node I also have the result. Next. So here, I'm going to introduce this equation here. Now, do you agree with me that this entire thing here is constant? Well, maybe if you're going to rewrite this code in the future, delta t may not be constant, right? But for a wide rectangular channel, this is constant. So I'm going to call this guy here Kc, just a constant term. And instead of having to write this down, just copy this constant and use it. I'm going to create this variable in my model, right? So what is this variable here? I'm going to define a variable here called Kc. And here I'm going to write with preliminary calculation that Kc equals 5/3 times S0 raised to the power of 0.5, slope, right? Divided by many number times the width of the channel raised to the power of 2/3. So that's Kc. So I don't have to be writing Kc again. I can just use this value. So in my kinematic wave equation, I'm going to use Kc. How? So for I equal to n nodes, Qn of II is going to be equal to the whole cube of II, previous time step, plus then this expression here, right? This expression is delta T, actually Kc, times delta T divided by delta S times K of II raised to the power of 0.4 times K Q II minus Q II minus 1. Yeah, there's a minus error here. You see this here, it was plus, but I sent this to the left-hand side of the equation. It should have become negative. So these numbers here are not positive, or negative. I know it's negative because this number here will be negative. The hydrograph flows higher, and because it's higher, this number is negative, but I have a negative here, so it sends a positive flow to the next. So this here is not plus, it's minus. Okay. This is it. Now, will this work? I'm writing the code with you here, so we're going to learn it. I also needed to update the old results with the new results. So I'm going to write in order for I equals 1 to n nodes. Next. And here I'm going to state that Q equals Qn. You see this location here? If you want to solve for the area, if you want to solve for velocity, hydraulic radius, everything, this is where you solve. After you take care of all the QNs, this is where you update the auxiliary variables. But we're not doing that. Instead, what I'm going to do is write the results. So how are we going to write the results? Result, write. So I know that the first cell I have to write result, row, is row 17. Correct? 17, 18, 19, so forth. So I'm going to write with the following approach. Cells 17, actually 16 plus I need another variable. I need a variable that marks how many time steps I have created. So then I can update where I'm writing. Okay, go back. Another integer variable in the nodes. I'm going to create a new variable here called NPS. Number of time steps. So I start with time t equals 0 and the number of time steps that I have equal to 0. Every time when I update the t, I update the number of time steps. So here NPS equals NPS plus 1. So whatever I had for time step, 20 becomes 21 if I have the next time step. So then I can write here in my results cells 16 NPS. So what time step am I now? Right? And that would be the first column value will be equal to NPS times dt. So however many time steps I have times delta t. That's my time, the correct time. Or I can simply write t. It would be the same. And for II equals 1 to n nodes, I'm going to write the results for calculation in the other cells. So cells, which cells? 16 plus NPS, column II plus 1. So that will be column 2, 3, 4. This is going to be, the value there will be to QII. So all the results will have been updated and written in the Excel file. I hope it works. That's the stuff. The code writing is this. So, should we try? Zoom back, because this is going to write a lot of things at the same time. If I click shadow routing, can you see the wave propagating? Cool, right? Let's make the computation longer. Let's make it 6,000 seconds. And calculate again. So at 6,000 seconds, if you scroll to the end, most of the channel is back to 2 cubic meters per second. But the end of the channel is still flowing at 4 because of the propagation of the wave. Now, I can make interesting graphs. For instance, if I plot the results here, maybe at 1,200 seconds, 36. This is the flow profile at 1,200 seconds. So downstream of my channel, it doesn't even know that I have a flood wave arriving there, but the flood wave is still growing in the beginning of the channel. So this is a flow profile. If instead I plot a column, okay, I have 101 columns, right? So if I plot, see here, 3,800 seconds, this is the flow hydrograph at that coordinate. So that's the change in the flow rate at that point, not the flow profile. We call it hydrograph. Hydrographs and profiles. So hydrographs is a vertical plot. Profile is a horizontal plot. Now, compare this graph, copy this graph here. I'm going to make the same graph here at 1 kilometer. So this is 4 kilometers almost. Let me plot at 1 kilometer. And I'm going to copy this graph onto this graph. Do you see that the shape of the curve is shifting, is changing slightly? If the delta t calculation was perfect, then this little bit of a vertical rise there wouldn't appear, but it does as a consequence of we having a smaller delta t than what we needed. Okay? If I make changes on the roughness of my channel, say 0.1, much rougher, and calculate, this is what I have instead. That I'm not deleting everything I should delete. See, because the time steps here now 25 seconds. If I change the roughness, the time step changes. If I make the channel less rough, calculate. This is what I have. Now, what happens if I use the FTCS scheme? We've had so much work to get it working, right? So a small change, which would be I+1 here, and 2 delta t here. So that would be 2 times delta t. That's the FTCS. 1, 4. Unconditionally unstable. There's no negotiation with this scheme. You always fail. We could have used the Lex-Friedrich scheme. Lex-Friedrich scheme, what I do, look at it, it's amazing. Lex-Friedrich scheme, you see this guy? I replace this guy with the average between the neighbors. That should be enough. So for instance, if I do that, 0.5 times Q I plus 1 plus Q I minus 1. So you agree with me. Now it's an average. I'm not using the point for the average between the neighbors. And I calculate not unstable. That is a different numerical scheme. We call the Lex-Friedrich scheme. Tomorrow, when we're calculating our dam rate, we're going to calculate with Lex-Friedrich. So, what is Lex-Friedrich? Let me put some names here. This is the FBCS, bad. This is the first order upwind, good, works. But I can use this scheme called Lex-Friedrich, LXF scheme, where here I have 1/2 of Q I plus 1 plus Q I minus 1. So that middle average makes it work. And if you think this is arbitrary, if you think this is coincidence, it's not. It can be proven mathematically through von Neumann stability analysis. One is unstable, the other one is stable. Interesting, right? So we ended up today playing with a kinematic wave, which is the simplest open channel flow solver you can construct, with 3 different numerical schemes to see what the choice of even each numerical scheme impacts the solution. With this Excel file here, you can play with slopes, you can play with roughness, you can play different things and see how this affects. If you want to make changes in this file to make a more complex inflow hydrograph, to adapt that from a wide rectangular channel to any cross-section that you want, you can. But in my opinion, nowadays, the greatest motivation people use the kinematic wave in the past was because it was computationally cheap to compute. It was fast, it was cheap. You didn't need to have a powerful computer to go through the kinematic wave. Nowadays, our cell phones can do this very easily, right? So it's very accessible computation. Using the full Summanet equations nowadays, it's okay. It's not a big deal. Creating the code for a full Summanet equation, as you're going to see tomorrow, is also attainable. Tomorrow, I'm going to spend very much fewer time in the board writing equations, and we're going to spend much more time in writing the code, because the Summanet equation, full Summanet equation code is more complicated to write. So we're going to spend more time writing this code together. I'm going to do like we did today. Sit down here, write from scratch. And then we're going to test for the case of a dam break. And the reason of a dam break is mostly because dam breaks are easy in terms of initial conditions, boundary conditions. They're easy to simulate. We're going to make this little code tomorrow. Probably we're not going to have enough time to play with different numerical schemes. This Lex-Friedrich scheme that you've seen here is the simplest and most versatile scheme that you can use for finite difference. Reason being is that here we know that the hydrograph is coming from the upstream to the downstream end. So when I'm writing this, look at this term here. I'm neglecting whatever comes from the downstream end. It doesn't matter, because nothing comes from there. But in a real channel flow, you don't know where the influence is going to come from. Maybe upstream, maybe downstream, you don't know. So you have to have a scheme that considers information from both sides. Well, this scheme here, FTCS, does, but it crashes, so you can't use it. This one does and don't crash. So that's why we use this. That's the simplest, we call it centered schemes, the simplest operational centered scheme that we can use. That's why it's so popular. That's why everybody who begins coding computational hydraulics begin with black string, because it's simple and works. Okay, so we're stopping here as usual. 10:40. I'll go along beyond the time, but we managed to create from beginning to end a simple open channel flow solver in Excel. I'm sending you this file for our list if you want to compare your code with my code, though I think it should be the same. And tomorrow, last day, right? So we're going to make this open channel flow solver. Tomorrow, reread there was a purpose today for me writing the sum equations. The homework for tomorrow is the following. Write those sum equations, assuming a rectangular, not wide rectangular channel. So instead of writing that equation in terms of Q and A, write that equation in terms of Q and age, depth. See if you can write that equation in terms of age by yourself. Because this is the variable we're going to be using. Age, depth of the water in a rectangular channel. But it's not going to be a wide rectangular channel, any channel. Rectangular.